This is lecture 8 for chapter 5 of Calculus 3, and in this lecture I'll give some examples of line integrals. In the previous two lectures I derived the expressions for line integrals of scalar fields and then the line integrals of vector fields. In this example I'm going to calculate the work or the flow integral along an open path. And here's the integral right here. F composed with R, this is the vector function composed with the parameterization R, and then you have a dot product onto the first, or the time derivative of the parameterization. Here's the path, t squared in the I, 3t in the j, and 2t cubed in the k. No significance to it, it's just the path. So here's the force field, 5xy in the I plus y squared in the j minus z in the k. First thing I want to do is compose the vector field with that path, and this is what I get. Now I have the vector field in terms of the parameterization variable t. 15t cubed in the I plus 9t squared in the j minus 2t cubed in the k, if I did that right. Looks like marginally like I did it right this time. Okay, now I need the r dot. You see the r dot is right here. I need that r dot. So to get that, I take the derivative of I take the derivative of the r, which is my parameterization. Here's the first derivative, easy enough. Now I just dot. That's actually written a little bit wrong, although not entirely wrong, so let me try to write it correctly. This would be F composed with R dotted with R dot. In other words, the integrand. That's what this is. 3t to the 4th plus 2t squared minus 12t to the 5th. Okay, note that this is a scalar. The dot product yields a scalar, and I'm going to integrate that scalar. And obviously that's simple. So the work over the first 3 seconds of pushing something along that path in that particular force field turned out to be 243, whatever. Okay? Now let's do another integral. In this case, we're going to look at the flux and the circulation on a unit circle. So the circulation is that tangential component, the flux is the perpendicular component. So here's the expression for the flux, and here's the expression for the circulation. We just did the circulation, but in that previous example it wasn't necessarily a closed path, and work could be done over a closed or open path. Doesn't matter. Okay, so we want to go around the unit circle. That's a circle of radius 1 centered at the origin, and that's the expression for the unit circle, but it's parameterization in terms of t. We just use sines and cosines. And 0 to 2 pi will take us all the way around, and you'll notice that we'll be going in a counterclockwise direction. This is a simple path traversed once in a counterclockwise direction. We're going to need that first derivative. Well, I'm sorry, the derivative of r. It only varies with t, so it is the first derivative, not partial but complete first derivative of the parameterization. That of course is minus sine ti plus cosine tj. And now in the flux calculation we need that normal. The normal is r dot cross k. Again, set up these three-dimensional vectors, the three-dimensional matrices to take a cross product. Your ijk is up here, then the r dot appears here, then k 0, 0, 1 is here. There's no I or j component, there's only 1 in the k. Taking that cross product, we get a vector, and this is the normal vector, not necessarily a unit vector. In this case it is, but it doesn't have to be. That's okay if it's just the normal. So here's our first example. We have all the pieces for this parameterization. We worked those out previously, but we need the vector field. Here's a vector field. Compose it with the parameterization. Maybe you forgot what the parameterization is. Let me write that here so you know what it is. Here's a parameterization. We're just going around the unit circle. R of t equals cosine t in the I plus sine t in the j. As t varies from 0 to 2 pi, we will trace out that circle, the unit circle. So I've composed it with f, and this is what I get. Remember, y, every place there's a y, I put sine t, every place there's an x, I put cosine t, and that's what I get. So I still have a vector, that's fine. The normal, we know that already, and now this is really, I shouldn't have written it like this. F composed with R, dotted with n. This is the integrand for the flux calculation. So when I take this dot product of these two vectors, then I get a scalar. That's what I need. And here's my scalar, 2 cosine t sine t. And for the flux, I just integrate 2 cosine t sine t dt, and if I go around once around that circle, it's 0 to 2 pi, end up with 0. That means the because there's a vector field associated here and it isn't necessarily 0 everywhere, this means the amount of flux entering the circle is equal to the amount of flux leaving the circle. That's one way you can get 0 flux, 0 net flux. And now let's do the circulation. For the circulation, here is the here's the integral. So we have, again, I neglected to, that's okay. I should have done f composed with r dot. This is the integrand for the circulation integral. Okay, so I substitute that in here. I know what it is. Substitute that in here. It's a scalar again. You got a dot product. It's going to give you a scalar. And then you integrate from 0 to 2 pi, taking you all the way around that circle, and end up with whatever, minus 2 pi. Just means it's actually going in the other direction. It's going clockwise. Well, we integrate it counterclockwise. Okay, so that's the flux and the circulation for that particular vector field. Here's the same calculation for another vector field. Let f be minus x in the I, minus y in the j. Same circular path. So when we compose it, this is what we get, minus cosine t in the I, minus sine t in the j. Now to get the normal, here's the normal vector, we have to take this and dot it with the normal, okay, and we get a minus 1. Fine, so we can integrate that from 0 to 2 pi and get minus 2 pi. And now for the circulation, we need, again, that f composed with r that we already worked up. So we're taking f composed with r dot at r dot. Actually, ends up to be 0. We don't have to even bother integrating that. That's 0. So I did two cases. One in which, well, not counting the first example I did, but of these last two cases on the unit circle, one had 0 flux out, net flux out of the circle, and the value of the circulation was minus 2 pi. In this case, the flux, net flux out of the circle, was minus 2 pi, but the circulation was 0. And it was 0 because there is no tangential component to that field along the unit circle. That's why that dot product is 0.